I start recording the session. So welcome everybody to our regular VSA webinar. And thank you for joining us today. So I like this kind of constant presence of the core group of people. So great to see you all. A couple of announcements before I leave the floor to Paxon, who is the main presenter today. First of all, so, the schedule of the seminars until the end of March is available on the web, and I my idea is to take a short break after end of March and maybe resume again in May. So to collect, so to recruit new speakers, maybe to give some time to the community people to produce new results. If you have any objections to this, please shoot and well, write me an email if you have any urgent material to present, so we can always accommodate your request. But otherwise, we run the sessions until the end of March, and then take a break maybe until mid-May, so and resume with the summer sessions we ran last year. The last announcement is that the next webinar will happen in 1 week time, not in 2 weeks time, but in 1 week time. And this is due to different reasons, but so just observe that the next webinar will be given on 1st of March, so next Monday. So this is my last announcement, and I'm happy to leave the floor to Paxon Frady, and so welcome.
Okay, great. Thanks, Evgeny. Yeah, so I'm Paxon Frady. I'm a researcher at Intel now, and still affiliated with the Redwood Center at UC Berkeley. And today I'm going to be talking about these kind of complex valued variations of hyperdimensional computing and some of the research we've been doing into how to use these variations and sort of like what you can get like when you think about complex value numbers. Okay. So yeah, so I mean, I'm not going to really tell you anything about any Intel product, but you know, don't sue Intel. So in the deep learning world, there is a literature emerging where they're realizing that you know, deep neural networks can't deal with these really simple transformations in images, and so you know, so they just like this. They have these images with objects, and they can just arbitrarily move these objects around in the scene. And if they show this deep neural network the object in this awkward pose, it's completely fooled by it. And they do a really thorough job of making sure it's been exposed to like the right poses, but of different objects, and trying everything they can to get this deep network to deal with these basic transformations. But it's a challenge for them, and for us it's almost easy, right? I mean, you can you see that it's a school bus, and you can even tell it's kind of poorly photoshopped, but your brain just automatically is able to extract out these basic geometric transforms without without much effort. And so then there is a kind of group of people that are working towards incorporating new machinery into neural networks so that they can they have the ability to potentially account for these types of transformations. And so I'll just point you to one kind of recent paper from the Redwood Center that also kind of goes about this idea, but just from a more like purely mathematical extracting these kind of concepts from Lie theory and Lie algebras to also like, incorporate this machinery into neural networks. And I'll try to explain how like what we're doing with VSAs is actually quite similar to this. But basically what they're saying is, so even with like really simple transformations, like, numbers just being horizontally and vertically translated or just being rotated and scaled, even these really simple transformations are fooling deep neural networks. And so what they kind of are proposing is sort of like a different type of generative model of a scene, where typically, like when we think about a generative model of a scene, we're talking about there's some kind of coding matrix which has about all the basis functions of the scene, and the scene is some sort of sparse coefficients of these basis functions, but then what they're adding is this transformation matrix. And so but this transformation matrix is itself parameterized. So like you need to know this, what this S represents is sort of how much of the transform is applied. So like this transformation matrix might be a permutation to like move the object horizontally, but then it's also parameterized by this S value, which is telling you how much to move horizontally. And then if you add a second dimension, you need a second parameter and another matrix to tell you how much to move like vertically. And so it's like a really powerful way to incorporate this kind of extra machinery, but this is sort of a strange thing to do in normal neural networks, because we're literally taking this vector S that parameterizes the matrix, and then we change all the matrix weights like kind of on the fly, and then you do a matrix multiply. So this S is like modifying a matrix in this strange way. It was like you're taking neural activity to like immediately change its synaptic states. So it's sort of different than what is in deep learning, where you almost have you have like these static weight matrices and you only update them in a learning phase. But this is more like a dynamical update. And the key too is that you have to actually infer multiple things simultaneously. So for this machinery to like work, and they also talk about like learning, but whenever you learn, you have to do the inference. And so that means you need to solve for alpha and you need to solve for S at the same time. So you're given this like image, which is like a 6 translated to the right or something. So you need to solve for like the fact that it's a 6, which is the alpha, and the fact that it's been translated for the right. And so it's not a trivial problem, especially as you continue to scale this up to more complicated problems. Like, if you want just translation and rotation together, then you need 4 of these matrices, and you need to simultaneously solve, 5 different variables. And so then as it gets more complicated, the actual inference part becomes kind of the bottleneck and the computational challenge. And so, one thing we can do though as well is use vector symbolic architectures to represent these transformations and transformation parameters. And so essentially, like in the VSA way of doing this type of thing, it's like we're going to replace this matrix with a VSA binding operation. And so you get some of the same types of properties by putting a binding operation here instead of this kind of dynamically allocated matrix. So just, I guess, most of us are familiar with the basics of vector symbolic architectures, but just like a quick high-level overview of, for one, there's been many proposals of different flavors of vector symbolic architectures, meaning like the atomic vectors are represented by different distributions of random vectors. So I like always like introducing the bipolar version because it's very simple and it's like pretty straightforward, where you use these random vectors of +1s and -1s as your atomic symbols, and they're very high dimensional, and just the consequence of that is that any 2 random vectors are going to have a small dot product. They're essentially orthogonal. with high probability in the high dimensional space. And so you can measure the similarity between vectors just by their dot product. So yeah, if two vectors are orthogonal, then they're different and you get a low dot product. And if two vectors are the same, then you'll get a very high dot product. And then the VSAs have this algebra. So there are different operations that you can use with these vectors to combine them in ways that enable you to represent all sorts of types of interesting data structures. And so it's not just that you're representing the atomic elements in a VSA vector, but you're also representing like relationships between them, or you're representing them inside of a data structure. And then these binding and permutation and addition operations allow you to kind of express those data structures using like algebraic framework. So basically then, the different flavors are very similar. And we showed in our 2018 paper how they have kind of the same amount of information capacity. So if you try to jam a bunch of symbols into these high dimensional vectors, you get this phenomenon called crosstalk noise. And but it's sort of like the same amount of crosstalk noise regardless of whether you're representing the vectors with bipolar states or if you're representing them with real valued states or complex valued states. The geometry and the crosstalk noise is essentially the same effect. So it's sort of, just, this is why a little bit why, all these different flavors are kind of coalescing into a single concept of vector symbolic architecture, because the geometrical properties of the algebra are pretty much the same. And then in particular, Tony Plate and early on kind of proposed this complex valued vector representation. And it feels to me like it's almost an accident, because he was really thinking about his real valued version, but he realized, like, to implement sort of the operations required, he would often just be taking a Fourier transform and doing things in the Fourier domain. And then he kind of just realized that he could just always just stay in the Fourier domain and just like kind of constantly do everything in this Fourier space. And so he also proposed this complex valued version of vector symbolic architecture. So just like just to give you a little bit of a sense of a flavor of like how to design algorithms and think about VSA architectures, and also kind of this points to like where they're actually valuable over just doing something conventionally. Is this paper about random indexing? So basically, what they did here was they want to like kind of come up with some way to like statistically understand different languages, and essentially the idea was to look at the statistics of these 3-letter sequences. So we call them trigrams. And so you take a big corpus of text from a particular language, and we're going to analyze each of the trigrams. And so you can use the VSA operations to kind of come up with a simple representation of each trigram. So you take, the letter, so the trigram is a sequence of 3 letters. So you take the first letter, the second letter, and the third letter, and you combine them in this way where you take a vector. Every letter is represented by one of these atomic vectors, and then the trigram is represented by the permutation. You permute the first letter twice, you bind it to the permuted second letter, and then you bind it to the third letter. And then what this does is it gives you a unique looking vector for every sequence of 3 letters. So if I just flipped the order of the second and third letter, I'll get a representation V2, which doesn't look anything like the representation for V1. And this is just the consequence of the random vectors and the binding operations. And so then what you can do is essentially you just go through a text corpus of some language, and you accumulate these trigrams into a language vector. And it's not really a magical mystery of what's happening. You're basically just counting up the occurrence of the trigrams from this corpus of text, And you build up this histogram representation of all the trigram statistics in the language, right? And but what's special about it is compared to the conventional kind of way of doing it would be that you squeeze these statistics into a 10,000 dimensional vector. Oops. Whereas if you were just a normal computer scientist, you might just think like, okay, I'm just going to allocate a counter for every trigram, and I'm going to just, whenever I run into that trigram, increment that counter. Well, I mean, since there are actually 27 cubed possible trigrams, you'd have to implement a counter for each one of them, which is even higher dimensional than this high dimensional vector. And so the reason that it can work is because typically there are out of these 20,000 trigrams that are possible, most of them just never happen, right? There's like Q, Z, Y, and all these sequences of letters that just it just never occur in natural language, and so you just never come across them, and so the statistics are actually quite sparse. So if you think about how many trigrams are present out of these 20,000, it's a very sparse subset of the full 20,000, and so in this sort of regime, this random indexing stuff can actually work and provide benefits. And so then, so basically, in the rest of their paper, they just create these letter vectors for different languages and show how you can use them to, classify a sentence into a particular language. And here they kind of just show how different languages, the letter vectors that they create for different languages have correlations that kind of make sense. So like, regions that have similar languages, cluster similarly in this vector representation. So in the complex domain, you can do, everything's kind of the same. So basically though, instead of representing the vectors with +1s and -1s, every vector element is a phasor, which means it's just a complex unit magnitude complex number, which is like a random arbitrary phase chosen for every element. And then the binding operation is still the same. So you're still just element-wise, you multiply these different phasor values, right? And the complex domain, that just means you spin the phases around. And so you're going to add the phases of the two phasors that are bound together. and so like a lot of times what we'll do is express this as an exponentiation. So unlike in the bipolar version, if you take two phasor vectors and you bind them together, this also results in just like a unique looking vector. So you can represent this quantity v squared by just binding v to itself. So then what we realized is that in the complex domain, this idea of binding then is you can define it continuously. And so it makes sense to be able to exponentiate v to a power that isn't an integer. So you can do this thing called fractional binding or continuous binding. So you can you just essentially spend the phasors proportional to this exponent, right? So you just you can put a real valued number here and spin the phases around, and this allows you to do binding continuously in a sense. And we like to call this the exponentiation trick. So essentially, if you want to come up with a representation of a continuous value, you just sort of pick a random phasor vector as like the atomic symbol, and then you exponentiate that vector with this continuous number. And then what this does, it allows you kind of represent manifolds, and you need these two kind of properties to effectively represent a manifold, right? So you still want points far apart in the manifold to be distinct and indexed by different patterns. So So if you just go even a single integer away, v squared is essentially orthogonal to v. So you still get the same kind of binding properties. But if you go only a small distance, then you get the smoothness property, right? So things that are close to each other on this manifold, you want them to still be represented by similar vectors. And so that's exactly what happens when you do this fractional binding. Is if you only increment this like to 2.5, well, v to the 2.5 still looks a lot like v to the 2, and it also looks a lot like v to the 3. So you get this like smoothness and interpolation ability by kind of doing this continuous binding operation. And so then, one thing you can do that's like much analogous to what Penty and Joshi did was create like distributions. And in this case, we want to know like the statistics of a continuous number that we sample from a distribution. So if you think about these samples that are coming from a continuous distribution, they're delta functions. And so what you do in sort of the just normal statistical litter is what you call a kernel density estimation, and which basically just means that you take those delta functions and you convolve them with something like a Gaussian. And depending on the kind of, the standard deviation of this Gaussian, you can either get this distribution that's like, too peaky because you're just like convolving across these delta functions, but there's still like a lot of peaks, but if it's too broad, then you might see a distribution like the green line that's a little, over flat. And so basically though, you have to figure out how to find the right bandwidth to convolve with this distribution. And basically that can be represented by just like a symbol alpha coefficient in this exponent. So if you make alpha larger, then you'll get higher frequency kind of kernel, and so you'll have these like more peaky things. If you make alpha smaller, the kernel gets wider, and you'll get like a smoother kind of approximation of this distribution. And then what's great about it is, in the same sense, is like you can do this conjunctional type of representation. So then if you want to represent the joint probability distributions of a bunch of variables, you can just encode each of these variables individually with their own kind of atomic vector, and then you do the exponentiation trick for the variable's value, and then you just take those vectors and bind them together, right? And then if you just accumulate these things into this big V vector, then this V vector is representing this joint probability distribution of all these values. And then you can query it for your Bayesian inference or whatever. So basically then, this is sort of like the idea about how to represent also like continuous things like translation. And so I'm going to kind of describe to you two like little models we're working on, where we use this exponentiation trick to essentially describe two-dimensional space. And so one model is kind of like a hippocampus model. So just where we want to track, your allocentric location as you move around a two-dimensional box, like a mouse in neuroscience, and but also just like a simple scene of like pixels, like I was showing you before, where you have these like letters that are just displaced in the scene, and you have to infer, where the letter is and what the shape is, and actually in this case we added a color dimension. So you can also color the letters and represent their colors by another kind of VSA vector. So you just so you have like H and V for the horizontal and vertical position, and then just another random vector for the color. And so you can just index an image this way to sort of represent it in a way where this idea of translation becomes possible to implement. So basically, you're giving every pixel in this image sort of like a VSA address. And so every pixel, it's just like a 40, 30, there's a cyan pixel, So that means the blue channel and the green channel are on. And so then the h to the 40, v to the 30, and the each color channel will be multiplied by basically the intensity of that pixel. And so then the intensity value is attached to this sort of VSA representation of where the pixel is in the image. And then you just put in superposition all of the pixels that are active, and you get this high dimensional vector representation of the scene. But like what's important about it is that you can now use the binding operation to translate everything in the scene, for instance. So you can take the atomic vector for this horizontal position, and then you exponentiate it by this sort of delta x, which is how much do you want to translate the scene. And then you take that vector and you bind it to the scene vector. And so this h to the delta x will just distribute throughout the sum, and then it sort of gets absorbed by the h vector. And so then you get h to the x plus delta x, which is now encoding the scene. And so essentially just by binding this delta h to the delta x to s, you've translated the image, okay? And you can do this in a pretty interesting way where delta x is continuous. And so if you translate something like a fraction of a pixel, then essentially what happens is it interpolates. So the one pixel starts to go down and the neighbor pixel starts to go up, and they sort of like kind of average out. And then as you keep going, the original pixel falls all the way back down, and then the neighbor pixel reaches the top, and then it kind of keeps going like this. And so just is basically just sub-pixel interpolation. So then you can see like what this interpolation is by looking at sort of the statistics of what happens when you start spinning these phasors or these atomic vectors. And so basically what we're looking at is we want to look at the similarity between the vector z and the vector z offset by some number d. And for one, you can show that this r, the z to the r, doesn't matter. So it's sort of like independent of where you start. It's just a function of how far away you are from where you started. And because when you do the similarity, you're just taking the conjugate of the one of the vectors, and so r just subtracts some r, so they just cancel out. And then what you're left with is just some z to the d, and then you're wondering how close is this to the all ones vector. And so like if d is 0, then everything is 1, and you get a very high dot product. But then as d goes away from 0, you can show just like that the probability distribution of the phases shifts away. It has this like essentially square distribution, and then the sort of like the characteristic kernel for this like rectangular distribution is actually the sinc function. And so this is like a really common thing you see in Fourier analysis, and it's sort of a miracle in the sense that it just like pops out of this. It's pretty interesting phenomenon. So what happens is, so then this is like empirically like what happens. So I take some random complex phasor vector x. I started with x to the 5th, and then I'm going to just compare it to x to the little x, and then just move little x continuously through this x-axis. And so of course, when little x is 5, then I'm just comparing x to the 5 to x to the 5, so I get a high dot product. And then when little x is 4, when it's 6, it's fallen all the way down to 0, and so there's a very, very, very low dot product. But when you look at this like continuous space between the integers, it traces out this blue curve, which turns out to be exactly the sinc function when you take the dimensionality to infinity. And it's pretty interesting because then there are these like pretty characteristic like negative dips that happen like right on the outside. And you know, this is like not just crosstalk noise. It's not just some noise phenomenon. This really happens no matter what, even if, you know, the vector dimension was infinity. And you know, like part of the reason why I think it's sort of unavoidable to have these kind of negative tails is because of what's happening in the high dimensional space. And so if you just kind of look at this high dimensional vector space, and then I take like, essentially like I take 3 neighboring orthogonal directions in this super high dimensional space. So this would be like x to the 4th, and this vertical would be x to the 5th, and then the horizontal would be like x to the 6th. And then I'm just plotting this 3-dimensional space what the similarity is. You know, it traces out this curve that like sort of bends and it visits these orthogonal directions in sequential order, and sort of like as it bends, you know, so basically as it bends towards this vertical axis, it first has to kind of like bend away from it. And, you know, and this curve is like perfectly smooth and continuous from all angles and orientations. I could depict any, you know, 3 sequential orthogonal axes, and the curve would look exactly the same. And so this is like kind of a special curve that happens as you, so it's, you know, when you do this exponentiation trick, you're just kind of visiting these different orthogonal vectors in the high dimensional space, one after the other in this like smooth curve shape. And but then it also approximates to interpolation with a cosine. So if you just look between x to the 4th and x to the 6th, you get this curve which looks like almost exactly like half a cosine cycle. And so it looks like, you know, when you move from 4 to 5, it's the same as like interpolating the 4th and the 5th vectors linearly with weights, just like with a quadratic kind of cosine weighting of those 2 vectors. So this like exponentiation of the phasor vector is approximately the interpolation of like the 2 neighbor vectors. And so you can kind of see this also in the 3-dimensional plot, you know, just these semicircles that go from one axis to the other. And so you could imagine, you know, you just want to interpolate as you transition between those 3 axes. And that's essentially what's happening with this exponentiation trick. It's approximately interpolating. But the difference is like with these cosine thing, there's always a kink. So whenever you transition from one axis to the other, there's this like kink in the curve. But this sort of sinc function based curve like doesn't have this kink, and it's like perfectly smooth from all view angles. And so that's sort of the difference. But you still get, you know, but the idea is like you still get this sort of almost interpolation property. So then, so use this idea to then create the resonator network in a way that can handle these input scenes where, you know, yeah, like the data is really a generative model where there's a letter template, but it's positioned kind of arbitrarily in the scene, and, you know, it's given a random color. And so then, you know, we just described this resonator network. I kind of talked about it last time, so I don't want to spend too much time on it, but basically you can then encode the scene, like I was saying, and then you store in the resonator network these like templates for each letter. So let's say that like the Z's have all the templates, and then the these kind of position vectors, these exponentiated position vectors, you just store in these other code books. And then the resonator network then is what it's doing is like it's looking for a combination of the letter template and the location vector and the color that makes sense with the scene. And so it's like essentially searching through this pretty big combinatoric space. And in a sense, it's like kind of crazy because like the position is a continuous number. So it's like, it's even beyond combinatoric in some sense, but yeah, but basically it's like searching through all these combinations of factors to find a conjunction of them that sort of fits with the scene. And so when you get a scene with multiple objects like this, it usually like hones in on one object at a time, and then it like factorizes it, looking for like a particular combination. And so you can like, start to use this sort of thing as this inference algorithm. So like in any of these models where you have, machinery that you can perform these translations or just whatever geometric operation, you have to do this inference where you infer the object and the transformation simultaneously. And hopefully the Resonator network and this VSA stuff is, it could be a viable, efficient way to do this inference. And in our sort of benchmarking experiments, what we show is like this strategy of searching in superposition is actually, outperforms just these normal gradient strategies. So normally you would just set up a kind of a cost function and use gradient descent to sort of minimize the cost function. But the issue is just like there's so many combinatorics, and that means then this cost function has a huge, really high dimensional landscape, and it often just gets caught in local minima that aren't optimal. But the Resonator network, it doesn't do gradient descent. It's this, we show that there actually isn't like a normal Lyapunov function. And it really does this like stochastic kind of random search, and it has this like positive feedback phenomenon. For whatever reason, that just like enables it to search the space more efficiently. And we see in our benchmark just like, way more improvement. It can solve like much harder problems than sort of similarly parameterized gradient-based methods. So hopefully this can be part of the inference engine for sort of these ideas. But then like one of the big challenges, like kind of the next challenge, is really to try to like start really thinking about three-dimensional space and three-dimensional vision, and how you might encapsulate all these three-dimensional geometric transformations inside of these vectors, and then specify that in a way that could, you could use something like the Resonator network to infer all these factors. And when you go, you would think you would just go from 2 to 3 when you go from 3 dimensions, but it's more like you're going from 2 to 6 or 2 to 8, and then you need like even multiple different things because a three-dimensional scene, you not only need to think about like where things are in three-dimensional space, but you also need to think about the camera itself. So you need sort of an allocentric representation and like a global representation of the objects. And then you need to think about not only the object's three-dimensional position, but also you need its norm or some position, and it has a direction it's facing. So that's actually like a 6-dimensional set of parameters. And so for an object, if you want to like just draw the scene like in computer graphics, you need to know like where the surface is in space and also its norm. And then you need to know like the angle of light. And then so the angle of light multiplies with the norm, multiplies with the color, and then this multiplies with the angle of the camera. So it's like a pretty complicated set of conjunctions that you have to compute to like render 3D graphics. And ultimately the goal would be to just be able to specify all of these things in VSA language, and hopefully use the Resonator network to like solve the inverse problem, where we want to like take a scene and infer all of these parameters, like where's the light, where's the camera, where are the objects. And so this inverse problem is really the challenge. So then one of my goals is to try to like enable these architectures onto neuromorphic hardware, because this inference algorithm, even though the Resonator network seems to be pretty efficient at it, it's still a lot of computational work. And as we make the problems more complicated, if we want to get to three-dimensional scene understanding, then this inference engine is really like, it's just going to, it requires a lot of computation. And so if we can accelerate that with new hardware, that's going to be really powerful. but also I'm a neuroscientist. So I'm definitely just like really interested in kind of understanding the brain and describing the brain. And so one of the things we've been really excited about is how you can use spikes and spike timing codes to represent complex values and perform these complex value algebraic matrix computations. And so we have a paper describing essentially this idea where, you know, like I'm saying, that we have these representations, these vector representations where, you know, every entry in the vector is a complex number. And, you know, we need to do even complex valued matrix multiplies. So the vectors are complex numbers, and then also these like code books, you know, the cleanup memories, they're complex valued synaptic matrices. So we want to like do the full complex valued matrix multiply. And so then we show how you can actually represent the neural states actually with spike timing code. And so sort of the phase of the complex number is represented by the latency of the spike relative to some sort of, you know, reference frame. And then the phase of the synapse can actually be represented by a synaptic delay. So then with these kind of basic mechanisms, you can build, you know, these neural networks that can compute the complex value dot product and use that as part of, you know, the whole system. And then the other kind of front is a sparsity. And so with what I've been telling you, every vector is a phasor. Every element of the vector is a phasor. So it's like it would be like every neuron is sending a spike, you know, at every period of the cycle. But in neuroscience and also in neuromorphic computing, if we can minimize the number of spikes being transmitted, you know, that saves us a lot of energy. So we've also been looking into variations of vector symbolic architectures that are also sparsity preserving and naturally sparse. And so the idea is like instead of a dense vector full of complex numbers, we're going to have a vector that's sparse. So mostly everything is zeros. And then sometimes there's an active element. And, you know, we looked at, you can think about this as just a binary vector. So the active element is just one, or you can think about it as, you know, this active element is a phasor. And so we looked at these different ideas. So we had this idea of just a general k-sparse vector. So you just randomly, any entry in the vector can be on, but only k of these vectors are hot. And we show in this paper, you know, how like the binding operation is actually related to the tensor product, and it's often, you can think of the binding operation as a reduction of the tensor product. And so we came up with a way of, you know, so you take these two k-sparse vectors, you sort of like do the tensor product, and then you subsample this tensor product down back into the vector space, and so you can make, you know, so you don't like necessarily need to compute every element of the tensor product, but only some subset of it. And but what happens is if you use general k-sparse vectors, it just becomes impossible to actually invert them. So you can generate from two k-sparse vectors, you can generate a third one, but you can't generically go backwards without losing some information. It's just because there's holes in this tensor product that you don't always fulfill. But we then realized that there's, if you do a more structured vector form, so basically what we call the block code, basically, and so this was actually proposed before, but essentially every block in your vector, it only has one active element. So then you have k of these blocks. So then you have a k-sparse vector, but it's in this block form, and only one hot element per block. And then you can kind of localize the communication to within blocks, and then you get a binding operation that is sparse, and it preserves sparsity, and it's perfectly invertible. And basically what all that's happening is it's kind of like the phasors, but in the blocks. So you just take sort of the index of the active element of the two blocks, and you add the indexes, sort of modulo the block length, and that's the binding operation. And so with that, you can essentially do the VSA stuff, but with sparse vectors and this kind of local block-based binding. So then, like, we're trying to then, bring this a little bit to neuroscience, or like kind of also, if we're thinking about three-dimensional graphics, we need to sort of think about the camera and this allocentric representation. And so, like, a lot in neuroscience, there's this big literature about the hippocampus being this allocentric map. And so we were, if you put all these things together, we have these spike timing codes that are kind of based on this oscillation reference frame, and then we have like these sparse vectors, and this sort of clever way of representing continuous spaces. So we sort of wanted to try to link that with like hippocampus, and so basically what we're doing is we take in this case it's a little bit, this was done a little bit before we fleshed out the sparse block code, but basically you're coming up with this similar idea of like a sparse representation of space that has these exponentiation trick kind of vectors. So you essentially take these vectors or these permutation matrices or these vectors, and you exponentiate them with the continuous value of your location, and then you have this like neural population activity that's representing your location in space. And so then you can just sort of like plug this into a model and simulate it and see what happens, and see if this like matches neuroscience data. So essentially the idea is like, you just have a mouse. It's kind of, this is a standard experiment where the mouse just runs around in a box and it's like just looking at, whatever in the box, and you're recording from its brain. And then if you just do all this, machinery for encoding the location into a vector, then you can like see this spike timing code emerge, and you sort of like compare it to something like the theta oscillation, right? And so then you see, these neural activity patterns that, like, maybe you kind of look like something you would record, and then you see like phenomena just emerge, like phase precession. So it's well known in hippocampus that so you have these place fields. So you have place fields and phase precession. So basically, when the mouse runs into a particular location in space, then there's a neuron that sort of becomes active when the mouse is in that location. So that's a place field. So here's an example of a neuron that sort of has this place field over to the right, and another neuron up to this top left corner. And so like whenever the mouse visits this location, that neuron starts firing. But then also what they see is this thing called phase precession. So as the mouse kind of like goes through its place field, the spike timing shifts in phase relative to this background oscillation of theta. And so they call this phase precession. So at first the spikes are sort of late in the phase, and then as the mouse kind of moves through the receptive field, the spikes move forward relative to the global oscillation. And so this just happens in the phase coding, but there are definitely like a lot of things that are different still. And for one, it's like in this code, it's symmetrical. So typically in the hippocampus, you only see phase precession, but not recession. And so if the mouse moved through the place field in the opposite direction, in this model, the phases would just go in the opposite direction as well. But I think there's another way of kind of extending the model, and when you think about three-dimensional graphics, like I was saying, you not only need to know the location of the camera, but also you need to know its viewing angle, right? And that makes a big difference. And so you could we're kind of proposing the possibility that the hippocampus isn't just representing space, but it's also representing the viewing angle. And this would then kind of change the code, and the phase precession thing would potentially go away if you just sort of configure it the right way. And so then basically then you're just like adding more vectors together where you're representing location and you're representing kind of viewing angle, kind of in the same idea. The other clear evidence for this, and it's like in the hippocampus literature, you see often the place fields are direction dependent. So especially if you have a linear, like a linear track, and the animal can move in only one dimension. When it moves from right to left, it's a different neuron than when it moves from left to right. And so there is this direction selectivity component. And so you could think about that as a component that's dependent on the view angle of the mouse. And so then we wanted to try to show how, if something like this were true, it's not necessarily easy to see it, and it doesn't preclude like just the place cell things. You still get, place cell activity here, but it's also direction dependent. So it's a conjunction of view and place cell. And but then like we wanted to show how you could relate this to some of these new neuroscience experiments where they're recording from hundreds of neurons at once, and they're trying to like do statistics on the neurons, and so kind of what you see is that there's these different kind of concepts of the dimensionality of the neural activity. So you might record from 1,000 neurons, right? And this is like the dimensionality of our VSA vector, right? But then there's this like kind of tiling dimensionality, and this has to do with like how far apart do you have to be on this manifold for the code to be considered like to look different. And if you take your neural space and you try to compress it with like something like principal components analysis, then you'll get sort of eigenvalues that are significant up until the tiling dimensionality. And so you can think about this just as being like, how far apart are the kind of integer representations, and you grid out the space based on these like integer powers, and then you get the tiling dimensionality. And so in this model, it was like more like 100, right? I kind of divided up the space into a 10 by 10 grid. And so if I PCA through the neural activity I produced, you'll get this like kind of 100-dimensional vector. And then what you can do also is these nonlinear manifold learning techniques, like one of them is kind of like isomap. And what these do is like they look for, what's really happening is there's actually just a lower dimensional manifold, right, which is like the mouse's location, or maybe it's the mouse's location and its head direction in conjunction, so like something that's 2 or 4 dimensional, and it's just like tangled up in this high dimensional space. And so then these manifold learning algorithms learn how to flatten it out, right? And so if you do that approach to this data, you can like recover the manifold dimension, which is really just like the fact that there's horizontal and vertical translation, and then potentially your viewing angle. And so then, yeah, you can like take the neural data, if you do isomap and kind of do it correctly, you can actually pull out then the 2-dimensional manifold. So yeah, that's basically what I want to tell you about. So these complex valued VSAs, they have this kind of cool property of continuous binding, and we think that has a lot of potential for representing and encoding continuous values and manifold structure. And whenever we talk about these transformations being kind of applied in our generative model, it sort of means that you have to infer multiple variables simultaneously. And I just wanted to point you back to the Resonator Network as potentially the machinery you could use to be this inference engine. And then we're moving towards trying to develop a new VSA that's essentially sparse. And there's still some issues with the block code that we're working out. For instance, if you try the block code is also, you can define it in this continuous manner. You can define the continuous binding operation, but the problem is that it doesn't stay sparse in the continuous domain. So if you take the block code, you bind 2 block vectors together, you get a block vector out. But if you do this continuous binding, the in-between states are like very dense. So you get this like kind of erratic activity in between. And so it'd be cool. And so it'd be nice if we had like a full binding operation which stayed sparse even for these continuous, continuous transformations. And so then there are a couple of papers there that you can reference. And yeah, thanks then everyone in the Redwood Center, and of course Intel. And yeah, I'll take any questions if you guys have it.
Thank you, Paxon. Great talk indeed. So many concepts. I mean, many new things for me personally. So I think I need to do some reading to appreciate the mouse part, the part about mices. I open the floor for the questions, and maybe I can start with a few questions of my own on the right, using my rights of the as a host. So first question. Oh, there is noise on the background. So this translation, with exponentiation that you presented, how does it work with the kind of 180-degree rotation? So when you have a mirrored image, so I mean, this is very typical in robotics. So when you turn 180 degrees and you need to kind of match the image to what you previously seen.
Yeah. Okay, yeah, so I didn't talk about this, but yeah, there is a lot of cool tricks you can do about sort of the topology of the manifold you're encoding. So yeah, if you just pick a random vector, then there's no real topology. But if you you can pick random vectors that are limited to certain distributions, and it's all kind of based on the identity vector. So if you have the identity vector is a vector of all ones, and you can take different roots of the identity vector. So if you say if you want if you want a topology that goes in a torus or a circle, then you can take, so say after 10 steps you want it to go back to the beginning, then what you do is you take a random vector where each entry is one of the 10th roots of the identity, right?
Oh,
So you
wow.
take the phase circle, you divide it up by 10, and you pick, at every entry, you pick one of those 10 values. And then that way, when you exponentiate that vector to the 10th, they all go back to the identity. So you can code topology like that. And then if you wanted a flip, what you do is you take the roots of -1. So then you have a different, so often, yeah, like if you had a Gabor function that's positive on top and negative on bottom, and you wanted to rotate it 180 degrees, it would have the negative sign. And so then you can take actually the code vector as a root of -1, and then it will go through +1, and then a bunch of orthogonal directions, and then -1. So you can, there's actually some tricks we have for different topologies, and it's just about you pick these code vectors from different random distribution than just a completely uniform.
Okay. I see. Maybe one more question I allow to myself to ask you. This sparse binding that you have presented, well, it's pretty much understandable. I mean, from the engineering point of view, but how much biologically plausible is it? I mean, so we know that computations in the brain are sparse, but I mean, this blockwise binding. So how does it reflect the reality?
Yeah, I mean, we're kind of disappointed that general k-sparse vectors they just can't work. It just doesn't. It's not perfectly invertible.
Yeah,
and,
yeah.
So it's more biologically plausible than you might think, because there are certainly like these modular structures in the brain, and there's also a lot of winner-take-all dynamics, and so that might actually be a little bit of evidence for like kind of a block code, but I don't know. It's not fully satisfying. It does feel a little bit too over-engineered for neuroscience. But yeah, but I think it's definitely closer than the dense version. And we have some other ideas, but yeah, we haven't fully fleshed them out.
Sure. Yeah, thanks. All right. So anybody else who have questions, please unmute yourself and ask.
Tony, were you waiting there?
Yeah, sure. Thanks, Ross. Edward, that's fascinating stuff. Thank you. A lot of interesting directions there. Had a couple of quick questions. One was at the beginning you were sort of looking at the different ways you could sort of spaces you could use for VSA. You mentioned the bipolar and the phasors, and I always saw an interesting sort of parallel between the phasor representation in complex space and the bipolar sort of +1 -1 as being the most extreme quantization you could do of that.
Right. Right.
But I could. There were always things about the bipolar that I didn't find that satisfying. It seemed to like you lose information in it when you do superposition. But one thing, the question for you I have there is do you see any way of making the fractional exponentiation work with the bipolar representation?
I mean, it's a little bit maybe hacky, but you could kind of do it. For one, you would want to think about it as more like a permutation, because yeah, I mean, again, if you just multiply two bipolar vectors that are the same, you get the identity vector, and that is because, like I was kind of saying, if you want these loops, then you take roots of the identity vector, and so if you want a loop of 2, then you take a square root of the identity vector, which is a bipolar vector. And but then, yeah, if you do permutation, then it's also kind of like a binding. And so you can just permute all the elements each time and sort of get this ordered, sequential, like different vectors for each power of the permutation. But then if you wanted it to be fractional, then you would have to do a fractional permutation, which would change. I mean, it would just change. It would look like, if you had like in sequence like a +1 and a -1, and you fractionally permuted it, then you would have to like average out the values and kind of interpolate. You would just do this interpolation in the values of the vector, and so so then you would lose the bipolarness. So they would have to like decrement and increment in magnitude kind of smoothly, but that would be kind of the same thing, if that makes sense.
Yeah. Okay, that's interesting. Okay, and then the other question I had was, you're talking about the sort of implementing the phasor operations with neurons, and you pointed out that phase can be the timing, and then synaptic delay can be essentially adding the angles. And so my question there is there any evidence from brain science of synaptic delay being something that can be learned?
There actually is. It's actually surprising. So I mean, of course, there's obviously synaptic delays all over the place, but maybe they're just there because they have to be there. I mean, it's just a physical thing. But I mean, for one thing, you could imagine a situation where there's just like a pool of synapses, and they sort of just have random variability on their delays, and learning rules select particular synapses that have particular delays, right? And so you prune away, you just like have all these random delays that you prune away from. But there is actually also neurophysiological evidence that shows delays adjusting. So you can kind of do these like, input output pairings, but you kind of lag it, and people have shown that you can induce variability in synaptic delays through these like plasticity mechanisms. And it's pretty subtle. I mean, it's only like a few milliseconds, but
Okay.
there is some evidence for it.
Okay. I wonder whether it could also be working through, if you think of synaptic magnitude and time to reach threshold, like the speed of attack could also be the useful information in there. Could be the delay, the time.
Yeah, that's definitely another kind of thing you can add to it, which would be like an integration time. And there's sort of like the capacitance of the neuron. If you could change those parameters, could also change delays. Yeah, but you have to like make sure you don't confound it, though. Sometimes like if you try to use the integration time, it might mess up a different aspect of the code, but it's potential that could be a mechanism as well.
Okay, thank you.
Yeah.
All right. More questions? Ross, you wanted to?
Paxon, yeah, hi. Great
Hey,
talk,
Ross.
loved it. Thank you very much. Another two-parter question, I'm afraid, but I'll put them both out together and answer as you see fit. This is about the resolution aspect. So, I mean, you did allude to it early on when you were saying that if you increment the exponent by 1 in one of these spatial representations, your x-axis, for example, so incrementing the exponent by 1 will get you to somewhere which is orthogonal to where you started off from. And so if you're with your original example you had of letters on a plane, you didn't say what the resolution was, whether you went to orthogonality over the entire length of the screen, or whether you only needed to move 10% of the screen in order to become orthogonal. Whereas in the mouse example you gave, you were talking about tiling, and so you gave the example there of having effectively 10 times going to orthogonality over the length of the dimension. So sort of the question 1 is about the design thinking behind choosing what's the resolution for some particular application. And then the other sort of the part B of the thing is, would it make sense to be working with the representation of a dimension actually effectively having multiple vectors with different resolutions simultaneously? So you might have one which went to orthogonality over the entire, and then another one which went in half the distance, and so on.
No, exactly. Yeah, we've been thinking exactly along those lines too recently. Yeah, so for the scene is actually the resolution is literally the pixel sampling. So I mean, yeah, we think about you think about the translation as being this continuous thing, but then your pixels are like sampling from particular points in this lattice, and so if you want the full pixel resolution, you want every pixel to be a unique vector. So then essentially the exponent is actually the pixel index in that pixel lattice. So it is like the sampling. It's sort of like the resolution of the sampling lattice is like what you want as the exponent.
Yeah, although if you were doing something, say, robotic, I mean, I'm presuming that in a learning sense, you want things which are neighboring to be treated similarly. So you might then want to have a lower resolution in your representation, so you get generalization across location.
Exactly. So, because like what we've been thinking about recently is like, yeah, I mean, you don't need to represent things as pixels anyway, and often we have like sparse coding or some other basis set that is like more compressed and actually sparser, which is good representation of an image. And so we've also been looking into just like a full Gabber pyramid, and so you'll have these sort of like edge filters, at different pixel locations, but they're also at different spatial scales. And then so then basically you would break up essentially the different spatial scales into their own lattices, and then every kind of Gabber at the different scales would just like have its different kind of VSA vector. And it'd be really nice if you could also, then take you have this kind of pyramid, and so I explained how you can like translate around one of the scales, but then in the Gabor pyramid, it'd be nice if you could translate like up and down the pyramid. And so like if you want to like zoom in and out of the little template, then you would want to like move along the scale part of the pyramid. So we're trying to figure out how to kind of do the same thing, but with like a full Gabor pyramid. So we can also account for like scaling, and potentially like rotation too.
Neat. Thank you.
Yeah.
All right. Well, despite the fact that we are running beyond the typical limits for the webinar, I'm very happy for this to happen. So if you have additional questions to Paxon, so please go on. So I keep the room open. So if any.
Yeah, just you can email me or just chat offline or too, and yeah.
Okay.
Oh yeah, I have also I meant to say like I put this on. I have this on a demo now. So you go to my kind of GitHub website here. It's a little crappy HTML page, but I have a full Jupyter notebook of this Resonator with the templates and all this stuff. So if you want to get some code and use it, you can find it here. And,
oh, that's great.
Yeah.
That's super. So we have a couple of, wait a second. So we have a question in the chat from Levi. So is this it? So he just publishes. So it's a TPAM demo release. So I don't know if
Oh no. Well, go down to Resonator Networks, and there's a so I have a bunch of demos for other papers as well on this website. So there's a TPAM demo, which is just the complex value detractor network with a spike timing code. And then there's a couple of other papers, but then in the Resonator Networks section, there is the demo for this scene analysis.
Yeah, so Sachin has put in the chat the correct link. Okay, listen, thanks again, Paxon. So great talk indeed. Thank you all for attending this webinar. So I think it's time to wrap it up. So we meet again in 1 week time. So it's important. So it's not in 2 weeks, but in 1 week time. So 1st of March, the next webinar. So stay safe and goodbye.
Thanks again, Paxon.
Yeah.
Bye.
Thank you. Bye-bye.
Bye.